difference in the constituent chiral quark model becomes infinite if you take it seriously, because there is no matching to short distance. In fact, there will not be matching to short distance for any coupling that is an order parameter. So that's not surprising that we have to put that coupling. So you may ask me, well, what is the interest of the Lagrangian then? I think the interest is that if you have complicated quantities, like, for example, the anomalous magnetic moment of the muon, where in fact the matching to short distance is done perturbatively, so there is the unit operator that is the leading operator, then the model, since it has gluons, has a matching which is relatively correct. And for those specific couplings, the model may not give you a bad answer. And that's why I got interested again in this model. Now, of course, there is still one coupling which is left, which is the quark mass, this constituent quark mass. Now, what value to take for that? Now, again, here, what I've been thinking about is the following. This model doesn't confine. So it has a spectral function. You don't believe the model in the timeline region, in the Minkowski space, but in the Euclidean region for moderate Euclidean values, perhaps the model is good. But doesn't matter if it is good. It's a field theory, and therefore values in the Euclidean are integrals in the Minkowski by dispersion relations. So if it is good, it means that somehow the areas that are reproduced by the constituent quarks want to be roughly the same areas that are reproduced by hadron states. So let me just, as an order of magnitude, try to fix this mass by demanding that the slope at the origin of hadronic vacuum polarization, which is this quantity I have here, this integral I have here, is match in the sense that the narrow width dominance of the rho matches the calculation with this constituent chiral quark model. That gives you that relation. And roughly you get a mass which is quite low. It's 225 with somehow an error, which by hand, in a way, and by determination of this coupling of rho, it has to be of the order of 25. So let me take that seriously and see what happens. Well, the first observation, and I was surprised myself, is that with this low mass, you get the slope of hadronic vacuum polarization. That's not surprising because I fixed it like that. But you get also this constant that Tony talked about of the correlation function, left-right, rather well compared to the phenomenological determination. And you also get one of the complicated constants of the effective Lagrangian of electroweak interactions, which has to do with the decay pi zero plus e minus, which is known also from phenomenology and from actually models of the type I described before, rather well. So this is encouraging. And that brings me to the last comments I want to make in the 5 minutes I'm left, which is what we notice in a way from discussions with Chimo and with other people is that in complicated calculations concerning, for example, hadronic Lie-by-Lie scattering to the G-2, the most sophisticated calculations are done with ideas which are very good, probably, but they are buried in very complicated computer programs, and it's very difficult to get a qualitative feeling if you have not been involved directly. And since there are still some disagreements between different approaches, the idea is, why don't we try to apply this model to this calculation, which is a simple model, has the merit of being a simple model, so where we can actually investigate the rough features and then see which sophisticated models are in disagreement or agree, at least within a reasonable error, with those ideas. This is what I would have liked to tell him. In other words, what we need is a simple, what I call a simple reference model to test other approaches. What I'm going to say here is the results I'm going to present in the last minutes are all very preliminary. It's work that I'm doing in progress with David Grenard. Now, let's look to hadronic vacuum polarization contribution to the G-2. This is the plot which shows the result of the anomalous magnetic moment from hadronic vacuum polarization as a function of the constituent quark mass. Now, for a mass, the lowest mass that I can think of from the previous determination will give me something like this 570 with no gluons, as compared to the 687, which is the value from phenomenological determination from data, from E plus E minus. Well, or even that is not too bad. let's say if we could get something like that for the hadronic light bypass scattering one, it will be nice. But what comes up to me as a surprise is that if you do the same operation but putting gluons with this coupling, you get a determination which is almost too good. I mean, this is 666 compared to the 687. And for a mass of 225, which is the middle value, let's say, that roughly I fixed from the other parameters. So that sort of is encouraging. Now, what we've done with David is to look systematically to all the hadronic vacuum polarizations, the one coming from two loops, electron and one loop, higher order hadronic vacuum polarization. I'll skip that and go very quickly to the last thing. So sorry about this cinema now. This goes, I don't want to pass too much time with this. Yeah. And let me go to the light bypass scattering, which is the subject that Shimo was work a lot. And it's my last interaction with Shimo was on the subject. If you look at this problem from the Constituent Chiral Quark model, there are two contributions. One is the exchange of the Goldstone particle. The other one is the quark loop. They are both contributions that are known because, of course, the model is known. In this case, the two features that I want to emphasize is that the contribution from the quark loop decouples as the quark mass becomes large, whereas the contribution from the Goldstone exchange grows as a logarithm square as the quark mass increases. So there is a competition between the two, which is the model reflects very nicely, and that's really QCD. Now, yes, I want to skip that too. Let me go to that. Let me tell you what you get from the exchange of the pi zero contribution. This is a contribution which, in fact, we know from first principles in QCD that in the chiral limit and in the Lorentz limit, this has to grow, as I said before, this has to go as a log square of whatever mass scale you have. So, for example, if you in the real world where the lowest state is the rho, if we let the rho mass go into infinity, this contribution should diverge as the log square of a rho mass. And of course, it plays a very important role in fixing the sign of the contribution of the orbital contribution to the hadronic vacuum polarization. And the coefficient is known. This is QCD. Now, from the Constituent Chiral Quark model, you also have this log square behavior. But of course, in terms of the quark mass, this time, it grows as log square of NQ square. For a mass of 225, you get this number. Now, that's not, let's say, don't compare these two numbers because this is just the number of the asymptotic behavior. Here, there are contributions which are logs, they are known to be negative and so on. So, but even if you just look at those numbers, they are not so extraordinarily different. Now, if you look at the constituent quark, as I said, it decouples as the mass goes bigger and bigger, and the contribution from a mass of 225 goes as, gives this result, 9.2, 10 to the minus 10. And since my time is over, I just want to flash you my last transparency, which is from the constituent quark. Remember, for a mass like that, I get something like this. From the pion exchange, I get something like that. The sum of the two gives me this number. I think that this model, you cannot take it seriously to a better than 30% error. So I put it by hand. I put by hand a 30% error to this determination. And I can see that, in fact, it gives me a very reasonable value compared to the work that we did with Shimo and Arkady Weinstein, which was a sort of recollection of all the different calculations. And this is the number which is considered as the reference number now for phenomenological applications, which was my last work with Shimo. And the fact that these are reasonably in agreement within errors gives me confidence that the ideas I have been telling here and that I would have loved to have Shimo's reaction to this gives us. So with those remarks, I will say thank you. And just let me say that very often I keep thinking about Shimo, and I miss him a lot. Thank you.